Assalamualaikum warahmatullahi taala wabarakatuh and a very good day. I greet everyone. My name is Muhammad Syamsul Imran Zaini from University of Malaysia Pahang. Today I would like to present about the effects of gypsum and vermicompost on aggregate stability of bauxite against liquefactions. In the West Peninsula of Malaysia, the bauxite mining area in the tropical climate state of Pahang was one of the main bauxite supplier to China, with the shipments peaking at nearly 1,766 million tons a month in the year of 2015. Due to that, the demand of large cargo to transport bauxite was strikingly increased as to fulfill the need of the market. However, transporting bauxite without proper treatment will lead to liquefactions and make the vessel to occasionally capsize. Therefore, liquefaction might occur, which is a regularly recurring phenomenon, occurring when carrying moist coarse grain, solid bulk goods on bulk carriers. Due to that, the stability of soil need to be implemented to avoid this kind of event to occur, which is subsequently in this present inquiry, the aperture is loaded up with the capacity of employing the mix of gypsum and vermicompost in bauxite soil as aggregate stabilizing agent, and another optional way to upgrade engineering qualities of the bauxite via optimization procedure. For this investigation, there are several methodologies that we follow. The first one, we determine the physical properties. The second one, we determine the chemical properties. Then we proceed with the aggregate stability test. And then we go to the flow table test. And then lastly, we test for the macrostructural characterization, whether we want to see the change in the microstructure that lead to the stability of the aggregate of the bauxite. As you can see in the table, table 1, which how we determine the physical analysis of the sample, which is as stated by Su et al. 2020, anticipated that adding gypsum to residue would minimize disposal by replacing sodium ion with calcium ion and promote aggregations, therefore thereby enhancing physical characteristic. But the data shows that the gypsum inclusions had no influence on total permeability. This discrepancy is most likely caused by the existence of pozzolanic chemicals in the leftover mud. For these agents, the mud hardens when dry, and the particles created by crushing and sifting are very firmly linked together and not prone to sodium ion in this dispersal. For specific, the particular results revealed here do not rule out the likelihood of higher impacts of gypsum and natural metal inputs, encouraging aggregations, notably in the regions. This is particularly true for the fine, non-aggregated material developed when bright, solidified trash is crushed. Admittedly, experimental studies have shown that the gypsum implementations can enhance the microaggregation and macroaggregation, as stated by Zhu et al. 2017 and Li et al. 2018, and that when the residues are left in place for an extended period of time, there is an improvement in microaggregation and macro aggregation, and it decreased in the quantity of fine portion present. From the bar chart, it can be concluded that the main focus of the study is that the Al2O3 is less affected by the liquefaction risk during the transportation of the bauxite in the bulk cargoes. The apparent concentrations and percentage of aluminium in the sample bauxite were determined by using the ETX. This information is critical for this step since the aluminium content of bauxite must be consistent before and after the addition of vermicompost and gypsum. Therefore, in the figure demonstrate that the usage of gypsum and vermicompost had no substantial effect on the chemical composition of aluminium oxide, the principal chemical composition of bauxite, and also the principal chemical composition of the bauxite. The control sample include approximately about 19.76% of aluminium, which is the real weightage of the sample from given bauxite. However, the sample of BA10604 optimization model shows the presence of aluminium content of 15.23% of the weightage from the amended bauxite. For the aggregate stability analysis, for the first figure, we want to determine the mean weight diameter MWD. So the highest MWD in fast fitting test is recorded on sample BC10604 at 1.548, whereas the lowest MWD in fast fitting test recorded in a control sample at 0.82, which was illustrated in the figure. The FW and WS test had substantial effects on the particle disaggregations. High MLD with the inclusions of vermicompost and gypsum indicated that the interaction between AB resulted to better aggregate stability to reduce the liquefaction risk. As for the second figure, we want to determine the height, the value of the erodibility factor, which is the height value of erodibility factor K indicate a less stable physical structure. Significant differences in K of the sample was demonstrated in that figure. The control sample was recorded to have the highest value of K in the fast splitting test, which is at 0.04, whereas the lowest value of K in fast splitting is recorded in B10404, sample at 0.024. The erodibility factor K embodies with both susceptibility of soil to erosion and disaggregation segregations as measured under the 3 disruptive tests. The factor reflected that different soil eroded at a different rates when the other factors involved were infiltration, permeability, total water capacity, and also the dispersion. As you can see for the flow table test, from the flow table analysis, the transportable moisture limit TML of the sample is 90% of the flow moisture point FMP. The TML of the specimen must exceed moisture limit stated in the standard to pass the requirement for bauxite to be transported. Therefore, the specimen from the same batch were tested to obtain moisture limit with the average value of 24.07%. This indicates for optimization model to pass the code by at most margin of positive 2.9%. Last but not least, the same imaging was carried out to compare the control macro aggregate B100 samples with BA10604 samples, as illustrated in the figure. So, the major fraction in the particles of 0.5 to 1 micrometer residue macro aggregates of control sample had a sheet-like form with numerous fine aggregate fragments. With the inclusion of gypsum and vermicompost, the number of macro aggregates of the sheet-like structure rose dramatically. The size of the sheet-like form increased greater, and the largest percentage detected at 2 to 5 micrometer particles. The introductions of the vermicompost and gypsum transform the bauxite to a denser structure. So the introductions of vermicompost and gypsum enhance the aggregate form from a sheet-like assembly to a prismatic arrangement as present of calcite in gypsum, whereas the 1 to 3 micrometer proportion of microaggregates dramatically reduced. As for the conclusions, the result of analysis shows that gypsum and vermicompost percentage by weight of 6% and 4% respectively shows the highest contribution in improving physical properties of raw bauxite. In terms of MWD, amended bauxite C10604 shows significant positive results, showing improvement from 0.882 mm to 1.548 mm. The total improvement was 75.50%, which greatly influenced its capability to disaggregate towards the external forces. Meanwhile, the improvement on its TML also gives a significant improvement from 20.67% to 26.61%, showing 28.73% of sample improvement, which passed the requirement as stated in IMSBC code. The initial water content of the raw bauxite recorded at 24.07%, which resulted to the TML value to be above initial water content, the meet requirement set by the IMSBC code. Therefore, it can be concluded that the bauxite stabilization using gypsum and vermicompost can give positive result to the MWD and the TML. So, by using stabilization of the gypsum and vermicompost as its own unique target value, it is proven that liquefaction risk of bauxite is decreased as TML of bauxite increase. So, using this approach, any soil with risk of increased pore water pressure can be stabilized using this set of experiments to obtain its own unique target value on using gypsum and vermicompost.